evil supervillain mode. Good. Okay, it's 15 past, and we still have a very low joining rate right now. Actually, no, now it goes faster again. Anyway, people are still trickling in. Very good. Well, let's start with not really service announcement. I mean that yesterday I sent out the emails for the plagiarism cases for the 4th assignment. So that means if you did not receive an email and you were expecting one, and I'm sorry to disappoint, we didn't catch you. And if you did not expect one, did not get one, well, double check your email, right? I mean, there's always a chance that you overlooked it, but probably you got off scot-free. So far so good. 8 people were not so lucky, out of which 2 groups, well, they're sadly not with us anymore. So that means that we're now, I think at the top of my head, at 59 people, individuals who had a warning, which is a ridiculously high rate, I would say. But yeah, well, then again, right? I mean, that verbatim copying, we really do not condone this. And for most of you, this should not be a worry. But for next year, we're going to be a little bit more strict and also catch those people that are close to verbatim copying, right? Not just word by word, but because we have plenty of cases where we know where you've been shopping. Okay, good. Then let's see. We have asked you by email and through Discord to fill out a form regarding your availability or possible, lack thereof, regarding examination. I mean, that's on the 25th of February, late March. The possibility for written exams. I mean, we're still in process of deciding who, what, when, where. Don't get me started. This is the stuff from my side for nightmares, what decision to make, the support that I have, and well, let's put it this way. I mean, that's the thought of 160 oral exams that makes both Professor Valera and myself cry. Then again, it might be the only option, and yeah, that's. Other options we are considering is running exams over Moodle, but then I hear all the people complaining that Moodle tends to crash after half an hour, and I do not want to think about running an exam and after half an hour crash, and then with 160 having to make a new exam. So anyway, these are nightmarish times, not just for all of you, but also on our side, right? So pity me. Good. Okay, then. Let's see, I'll just quickly over the chat. The things that are currently written there, I will answer later. And that's, let's get started with today's lecture. So last week, I ended with support vector machines, and we almost, but not quite, went over support vector regression. And so I'm going to quickly go over those slides. I mean, that this is a bit, let's say, plus material. And that's so it's officially part of the course, but it's really more in the advanced stretch, right? And that's so I can't say that we're not going to ask anything in the exam, but I mean it will not be, let's say, the main dish, so to speak. So let me then close my PowerPoint presentation for now. Because of course, if I would have now opened with lecture 10, then you would have been confused because are we now in last week or not? And I do not want to have confused students, or at least not right now. Okay, let me open this and let's go to the right slide. What do we have here? So where were we exactly? Radial basis. Okay, let me quickly start here then. From current slide, resize window, yep. And share screen. Good. Okay. Now, of course, it immediately, stupid Zoom, disappears. Then the chat window. Okay, now I've got that one back too. Okay, quick recap. Support vector machines. I mean that we had the separating hyperplanes. We had the max margin classifier. We had the soft margin classifier. And well, in the end, essentially what we're trying to do is in some potentially very high dimensional space, a low dimensional space, we want to find that plane, right? So that defined in D-1 dimensions, that cuts our space into half, right? Positive samples up, negative samples low, something like that. Now, the key trick of support vector machines is that we're not just going to do this in the plane input space, where such a plane may simply not exist, but we're going to do this in kernel space, in kernel land. What does this mean? We're going to take the data points that we have and we're going to apply some function over them. This function we call a kernel. And what this kernel actually does, it sort of transports our data, which may be, let's say, 2, 3, 4 dimensional, into some very high dimensional space. And the main trick there is that in this very high dimensional space, it becomes more and more likely that actually such a separating hyperplane exists. You can kind of imagine this, and I didn't explain this last week, but you can kind of imagine this, that suppose that we have now a linearly inseparable problem. Let me see, do I have a nice visualization in one of the next slides? Oh, here, for example, this one, in that here we have a linearly not quite separable problem, right? And that, now, suppose that we would magically add a column to our data, an additional feature xp plus 1. And with xp plus 1, all of a sudden, it is possible with our either our linear regressor or our, if we use nonlinear basis functions or nonlinear regression, to actually, by using this special feature that was magically constructed, all of a sudden it becomes linearly separable, right? But, so you can imagine if you have a 2D problem, right? I mean, that's just like this. And okay, we have now blue and red points sprinkled all together, right? I mean, that looks very festive, but it's impossible to separate blue from red. And suppose that we would magically have now a third dimension coming out of the screen that puts the blue ones all the way in the front and the red ones in the back. Then if you look at it from the front, they still look completely sprinkled, but by taking into account this third dimension that we now magically created, all of a sudden the problem becomes separable, right? If we rotate it, there's this cutting hyperplane in that. That is the intuition of what support vector machines or kernel machines in general do, right? But rather than adding this dimension by hand, because God knows what this thing should look like, we essentially project our low dimensional data into a much higher dimensional space. And if we use the right projection, then implicitly we have created this magic column, right? But okay, now here on this slide, let me not go back. I mean, that's the explanation of these slides you can grab from last week's lecture, of course. If, well, the data looks like this, I mean, look, well, linear, no, right? Not separable, and with some margin we can do it, but it's pretty bad. If we use the right kernel, in this case, a polynomial kernel would do well, a radial basis kernel would also do quite well. So this is the example for a polynomial kernel. Then what we actually do is we would like to have this curved decision boundary. Well, no such thing exists, right? It's a hyperplane, it's just flat, right? I mean, that's, but we transform the dimensionality of the input, dimension up to p, through our kernel function, which is just this fancy polynomial, right? I mean, that's written a bit weirdly, but okay, live with that, into this dimensionality psi, which we can also call as p prime because it's transformed. And in this magic, very high dimensional space, all of a sudden it's possible to have a linear separation. That's what support vector machines do. This is the key intuition that you need to have. This dimensionality psi that this kernel reaches, this can be, in the polynomial case, still countable. In that, so if we have a polynomial kernel with of the second degree, then actually we arrive in a p prime of 6 dimensions. So it is really projected much higher up in that. If we use the radial basis kernel, which I'll explain in the next slide again, the p prime is actually infinite. And you can show this formally. I'm not going to ask this of you, but there's infinitely many dimensions. And this infinity, right, this is where the key is. Because if I have to construct by hand this magic column, right, that I explained earlier, then yeah, okay, what am I going to do, right? But if I can come up with infinitely many columns, well, then one of them is surely going to be the right one, right? That is the let's say the intuitive trick of a kernel machine, right? Let's add all possible columns, and in such a way that we try not to overfit. There, I'm not going to go into details. Okay. Okay, so this is where we left last week, approximately, if I recall correctly. In this problem here, if we use a linear kernel, well, you can't separate, I mean, pink from blue at all, right? I mean, it's going to be a horrible fit. However, the radial basis kernel is essentially the kernel version of what you could say the k nearest neighbor classifier. kinda, right? I mean, that's, we had the local regression. We also applied a kernel over the k nearest points, right? I mean, that's, you may remember this from a few lectures back. This is all connected to the radial basis kernel. But essentially, for a point, what we look at the color attribution that you get from, well, not just the nearest points, but all points. But all points give you a, let's say, they vote towards what your color should be, what they think your color should be, depending on how close you are to them. So, for example, if we're wondering, okay, we are here, right, where my pointer is, which color should I be? Well, probably pink, right, by this data. These 2 points over here, the blue one and the pink one, right, they're approximately equally far away from me, right? And they will, under the radial basis kernel, which is essentially just putting a Gaussian over things. That's how you can think about it. Which is also what you see here in the equation. Both of them will basically vote equally strong to, okay, well, I think you're blue, I think you're pink. Okay, equally far, so the same contribution. Now, obviously, I have many more pink neighbors here. So in the end, the vote that my query point here should be pink is higher, right? But that is the general idea of the radial basis kernel. But, so the closer you are in kernel space, the more vote you get. Okay, now, if you put this to practice for a given data set, here we have the example for the hard data set, you need to choose a kernel, right? I mean, which kernel is best? Well, okay, hopefully you know the mantra by now, cross-validation. Wrong, because, well, you have 2 kernels, right? I mean, you can't really cross-validate them so well. I mean, you can test both of them and then choose the best one, but it's not like a parameter, like, okay, is it 1, 2, 3, which is the best one, right? There's really 2 completely different classifiers. And yes, you could test them through cross-validation, which the best generalization error, but a holdout set now also works absolutely fine. Okay, so if we now look at, for this data set, I mean, how similar, how good, or how bad does it work? I mean, as you see that LDA, the blue line, which you already know since quite a while, and the support vector classifier, right? I mean, that's, well, actually perform essentially equally well. But wait a second, now we went through all this math business, right? And we're now in infinitely many dimensions and whatnot. And don't we get anything for our money? Well, yeah, technically it outperforms it a little bit, right? I mean, that, but it's, your mileage may vary. So yes, it outperforms, but it depends, of course, very much on the type of kernel and how do you configure it. Right, so suppose that we do the radial basis kernel. I mean, that's we still have a parameter there, gamma. Basically, let's say the Gaussian, what's the variance, but then slightly different is how you can read it. Now, if we test it over, like, so the support vector classifier is the basic one, right? I mean, a bit better than LDA in this particular case, but not much. But now we have the support vector machine with a proper kernel. And as you can see, actually, if we choose the values right, the blue line, okay, then we have really much better performance than just the plain support vector classifier, right? And that, and if we choose these values wrong, so essentially if we spread the probability mass too far or too little, then actually we can get worse performance. So that is a bit shitty, right? I mean, that's so we have the power of getting a much better classifier, but at the same time, out of the box, it can also do something really stupid. Okay, good. That let me not go into too much detail because we also want to discuss the other topics today, of course, but not push too much to next week. There is a very clear and quite, well, say theoretically neat connection between logistic regression on the one hand and support vector machines on the other hand. That, I urge you to read this chapter well. I'm not going to go into the details today. That's because I have other stuff prepared in that. But essentially what it comes down to is that under, well, the right circumstances, they're going to behave exactly the same. That's weird because they're written completely differently, or not, if you now look at it a bit more in detail. This is for up. Okay. Can we also do regression? The answer is yes. The answer is yes. I mean, that, essentially, what you do with a So in support vector classification, right, support vector machines, having this cutting hyperplane makes a lot of sense, right? I mean, above the plane it's blue, below the plane it's red, or vice versa, right? I mean, okay, that is clear. And that you may want to have a decision plane that is, well, kind of curvy in your input space, right? Even though it's a really nice flat plane in the high dimensional space, sure, that you can also imagine, right? And that the choice of the kernel depends, okay, what curviness is allowed. Intuitively, this is all clear, I hope, right? But what about regression? How does that then work? Well, you can also do kernelized regression, and it is in fact one of the most powerful ways to do regression. And that's if you ignore splines and some of the other, let's say, advanced methods. I would still always recommend splines. I mean, that's just for the interpretability thereof. And I'm just going to give you the quick intuition of what does support vector regression actually do. Now, what you want to do in classification is create a plane such that, well, blue points here, red points there, right? I mean, it needs to separate. And in regression, we actually want to do the opposite. We want to have as many points as close as possible to this plane, right? Because then if you give me a coordinate on the plane, then I can project it back to the input space. I know what the actual prediction should be, right? And that's so rather than asking for that hyperplane with the maximum distances, let's just minimize it. So not much of a twist, right? Mentally, and that's and of course you well, there may be some outliers which we again want to penalize, but again the outliers are now on the other. Let's say we penalize them exactly the opposite way around normally. At the moment we have this, so we want to have points as close as possible to this line, right? And we still allow some margin. So within the margin we're kind of fine, but we want to sort of like minimize this margin in a way, right? And that's so the more small you can make the margin and the more of the points you catch, well, that is good, right? I mean, then you can predict them better and better. Now, the way to think about this margin around this hyperplane is to think of a tube, right? Just like a tube that you can sort of see through, right? I mean, that's and this tube is something that you can perhaps imagine that if you have a three-dimensional space, right? And that's what you now want to do. You basically want to have, let's say, well, sort of like a snake through your three-dimensional space, right? This is the tube. And in this tube, this is where you want to have the majority of your points. That is going to be your predictor, right? And the thinner you can make this tube, well, the happier you are, right? Of course, you can't always make it and still catch many of the points, obviously, right? Now, with that intuition, kernels distort the tube. In a pure linear regressor in 3 dimensions, well, it's just a line, right? Just a straight line. There's no curviness, right? I mean, that's okay, but I mean, what if our data is curvy, right? I mean, that's okay. Well, then we could use splines and whatnot and sort of and it becomes data dependent where we put the curves. Or we can use a kernel machine and through the appropriate kernel, basically not try to find this tube directly in our input space, but again, in data that is sort of magically padded with special columns that make the problem easier. That's what the kernels do. They essentially distort the tube. So in a way, well, let's see, what do we have here? Yeah, so if you have these data points, then this is the, what is it? Actually, yeah, so here, I think this is the better. So this is the tube that in the end you get on this data. I mean, if you sample more and more points. It is really the idea, you want to have your snake going through your space, eating as many of the points without moving its head. As little as possible. This is how you can think of it, right? And the type of kernel allows, let's say, the flexibility of the snake. That's how you can think of it. Good. Okay, so the important thing so far is that support vector machines can be used for regression, but that's, well, and I might ask you a bit about tubes and snakes, but I'm not going to quiz you on the exact mathematical details of these things. I mean, not in the exam, there you don't have to worry. But I do want you to be able to explain really well what is a hyperplane, what is a soft margin classifier, and so on, and the whole family, the whole zoo, right? On the classification side, that I want you to understand. Because if you understand that well, then you know the basics of kernel machines, and that translates to many, many other fields within machine learning. just to point out why this is so important, I mean, depending which school you belong, deep learning is nothing but a kernel, right? The neural tangent kernel is one of the current hypes. I mean, that, which, well, the main hope is that we have the power of deep learning, but at the same time, we have lots of the theoretical results from kernel machines, and then everybody like, okay, well, it's an ML-gasm in that sense. Good, okay. Unless there are specific questions on support vector machines, I'm going to skip to today's lecture. And I don't see any questions popping up. So then I'm going to find my other window again, and I need to resize it again because PowerPoint doesn't remember how I like things. And then I'm going to share the screen again. So, and now I need to dig up the chat window again. Good. Okay, so, well, déjà vu, lecture 11. And now it is actually January 28th. That's so what are we going to be talking about today? You're all way too young to have ever seen anything of Monty Python. I mean, that's, I mean, I'm also too young in that sense, or live, right? I see people shaking their heads, so you may know of it, right? That's, but hence, right now it's, and now for something completely different. Because up till today, we just started with lecture 11, we could have called the course Elements of Supervised Learning. That would have been a perfectly fitting title, and that's it's also for the course, right? It's a very unfitting title for if you look at what is the research that Professor Valera and myself are actually doing, because most of the research we're doing is on unsupervised learning. So, well, why did we then follow the organization of the course as such? The supervised stuff is in a way easier to explain, easier to grok, and well, it's about the elements of machine learning, right? So knowing the building blocks first and then going to the hard stuff, well, that's what we chose to do. Although we had long discussions, okay, should we not have more of unsupervised learning? And then we learned that this semester we only had 12 lectures rather than 14 or 16. And unsupervised learning was sadly the victim. And neural networks, Ravil, I saw your question. I'm going to postpone this to the end. That breaks the story right now a little bit. I'm not going to talk about neural networks right now. Good. So unsupervised learning. Why is it so difficult? We have no output variable. So up till now, we had x1 up to xp, and we wanted to predict y, right? So a target y. And now y is gone. I mean, we don't know why. We don't, in a way, actually literally don't know why what we're doing, right? I mean, we just have data, and we are essentially tasked with explain this data. I mean, this is my data. What can you tell me about it? That is, in a nutshell, the question that we're trying to answer. So another way how to phrase it is that I don't know what I'm looking for, but I'll know it once I see it. There's another way of putting it. That's actually quite fitting to today's lecture, because we're going to be focusing on something that neither Professor Valera nor I do in practice, namely visualization, but still something very important to know about. So what we want to find are patterns in the data. And like I said, if you don't know what the goal of such a pattern is, then it becomes much more challenging to do this in an unsupervised way than in a supervised way. If you know that you want to predict, let's say, which patients have cancer, right? Okay, then we just find those features that help to predict. But if we just have a database of, well, genetic profiles of tumors, or of what are we supposed to do? Well, there are lots of interesting questions. I mean, that you could say, okay, well, which genes tends to group together, right? If I see this one active, I also see this one active. I mean, there's clearly some interaction there, inference, right? I mean, this may be useful for later for a prediction task, but it may also be useful to identify, hey, wait a second, there's not just one homogeneous blob of patients. There might be 2, 3, 4 subgroups, right? And there's cancer subtype A, B, and C, which we didn't know yet. And if we now do know it, maybe you can have like a dedicated treatment for class A, because we know that for class A, these genes, if these are active, we have this drug that kills those genes or their activity, and everybody's happy again. And maybe for cancer subtype B and C, we're not so lucky, but okay, then we can do research towards that, right? And so on and so forth. So very useful to answer questions that we can't really pose clearly yet. Okay, so, well, yeah, so unsupervised learning by essence is more exploratory, and it's not just more difficult that you can't really judge so easily if a pattern, if a cluster, if something is good or not, right? You can't really say, does it predict? I mean, does it keep, let's say, the healthy people separate from the sick people? Because we simply do not know, right? We're not. This makes it also very difficult to assess the quality of the results, because there is no objective way, like what is good, what is bad, right? This is why, in my view, supervised learning, it's easy, it's trivial, right? And that's so give a person a measuring a yardstick, right? And all of a sudden we can maximize it. But in unsupervised learning, we have to figure out, our own yardstick. We have to see, okay, what is worth measuring, right? And that and what we will see in the course of today and next week, well, that is both really difficult, really exciting, and if you get it right, really cool. Okay, I already gave the examples that I'm going to skip. Today, actually, well, the most part of today's lecture is about visual data exploration. And as I already said, this is not really our research area per se, but it is something that you really need to know of. And that if you have any data, regardless of whether you're going to be doing a supervised task or not, the first thing you should really, really do is visualize it, look at it, right? That you will be astonished with how often you will catch stupid fuck-ups that you normally would have wasted weeks or days or months on, right? Trying to learn the wrong things, because there's outliers. There's actually very clear structures, right? Why are we trying to treat this as IID data when there are two structures that split the data into two structures, and so on and so forth, right? Or maybe the opposite. We think that there are two structures, but look, they're completely mixed. Right? That's okay. What are we to do there? Perhaps we need to get more features. Perhaps we need to use the right kernel machine, and so on and so forth. Right? We need to get things started. So so one of my favorite depictions of what is exploratory data analysis, what it's worth, it's basically it's the square zero question, right? So even before we get started, what are we supposed to do? That is what exploratory data analysis is about. Once we know what we want to do, okay, things become easy, right? If I tell you and solve this problem, unless I ask you to solve P equals NP, easy, right? I know what to solve. But before that, we need to learn. So another way of putting exploratory data analysis, it's trying to summarize the key aspects of the data in easily understandable terms. It's one of the definitions that you find out there by John Tukey, that's in the 70s. So, okay, let's go to summaries. Let's do something really basic. Let's go to summary statistics. Suppose that we have some attribute X, right? Just one dimensional, right? Super trivial right now, with numeric values. What can we say in very easy terms about X? Well, we could, of course, report the min and the max, right? And one of the natural things to say in addition, to say, okay, what is the mean, right? Well, you all know what is the definition of the mean, obviously, right? We just sum them up, divide it by the number of n, and there we are, right? But what does the mean actually mean? And pun not intended there. Obviously, it's the average value over the domain of X as we've observed it, right? And we use it all the time, but it's not a very informative value. So I consciously drew the example here at the top as such, right? What does this really say? I don't know, right? It's not really the value with, let's say, really in the middle, 50-50. It's not the highest value. It's just, well, it's the mean, right? It's also not robust. So the moment that we have some extreme values, right? Let's say my measuring device went completely ape shit and has a very high, very low value, the mean is going to shift. And that's very dramatically, possibly. That's very icky, right? So if you rely on a mean, you better check that there's no extremities, right? Extreme things going on. Here in these slides, I took them from a lecture I prepared a few years ago. I give the basic commands in Python. So this is not in R, right? Maybe it also works in R, I don't know. I speak many languages depending on well, when I choose to speak them. But if you're upset that it doesn't work in R, okay, just translate them. Maybe Google Translate works, I don't know. Next summary statistic, the mode. The mode of a distribution, hopefully you all remember what it is. It's not often used, but it is actually a much more interpretable summary statistic of your data than the mean, because the mode is that value that you see the most often, right? It's basically the peak of your distribution. It's also where the definition, if your distribution is multimodal or bimodal, it means it has two peaks or multiple peaks, right? If your data distribution has multiple peaks, then, well, it's useful to know where are these peaks rather than just give like, okay, this is the mean, right? This is the value somewhere in the middle. doesn't tell you anything, right? That one nice thing of the mode, in addition, is that it's actually very robust. Because, well, it's the one that happens the most, right? I mean, that's if I add a very low or a very high value, mode doesn't. It's like a honey badger, right? Okay, so what is also useful is the median. The median value is actually what most people think about when you speak about an average or a mean value, right? Because the median is the 50-50 value. It's that value in your data that 50% is higher and 50% is lower, right? But it's not what people mean when they say mean. The median is also robust. Very difficult to make it shift by just adding one or a few extreme points. You need to add a lot of them before the median starts to shift. Okay, now the median, just 50-50, does not say that much, right? I mean, it's really like a sort of a middle value, but that is that. I mean, what is also very useful to be aware of is what is the area, the interval in which half of my data lives. So what is the area around this middle value in which I can expect half of my data, right? Or whatever other percentage, but let's now stick to halves. And this is what quartiles give you. Very standard measure, right? I mean, that's hopefully you still remember it from other statistics courses, but still. What do the quartiles give you? The second quartile is just the median, right? This is why the whole buildup that I chose, right? This is just the median. And the first quartile, Q1, this is, well, the median of the left side of the median, right? I mean, and Q3 is the median of the right-hand side of the median, if you know what I mean. So now what we have is that we have now split our data into 4 parts, hence quartiles, and the distance between Q1 and Q3 contains half of our data, right? This is what we call the interquartile range that you come across now and then, especially in statistical literature, right? If you would wake me up in the middle of the night and say, well, interquartile distance or range, then I would also have to blink a few times and tell you to get out Sprite and ask me in the morning. But why is this useful? Because now finally we get to visualization, right? I mean, I needed to brush some things up and, well, make you aware that we're essentially, with all these statistics, we're summarizing our data in an easily understandable term. And then how does this relate to visualization? So normally we would be in a room and say, okay, let's have a raise of hands. Who knows what is a box plot or a box whiskers plot? And I assume that most of you would raise your hand. I mean, but don't feel bad if you don't know what it is, because here I am to explain it. The box plot, now I forgot, damn it. Who was again the box plot? Well, I think it was John Chuki, right? I mean, that proposed it, because I have the rest of the Eleanor's box whiskers plot by Chuki. Yes, exactly, 1970. Okay, then I can also tell the anecdote. I mean, not that I was there, but so John Chuki is really what was. I mean, he's not with us anymore. Let's say the founding father, king, whatever. I mean, and queen at the same time of exploratory data analysis. So he was basically really the one that says, okay, it's great that we have all these statistical notions for if, well, you have an idea, you have an hypothesis to test, is this hypothesis correct, right? Is it supported by the data or not? So rejecting a hypothesis or not. But what if we don't have an hypothesis? And then essentially all of statistics was just laughing. I don't know, why wouldn't we have an hypothesis? But actually he was right. I mean, in 99% of the cases, you don't have an hypothesis yet. And how do you get some ideas, some insight in your data? You need to explore it. So he proposed from the 50s onward in that many ways on how to essentially look at your data, either algorithmically or visually, in that, and sort of get some insight from it. And the box plot was proposed by him. And coincidentally, there was also another big statistician, big name, Box, and his name was Box. And well, he was rather upset that this plot was called the box plot. Okay, well, this is such a stupid plot, right? I mean, that's you know what? I'm also going to come up with a stupid plot, and I'm going to call it the Chuki plot. And that, well, he never managed to come up with a plot that was, well, perhaps a stupid one enough, but not as useful as the box plot. Anyway, stupid anecdote aside, I mean, but true story, bro. At least if you believe the history books. So what do we have here? What does the box plot do? Bless you, Marco. The box that we have here, this corresponds 1-to-1 to the quartiles that we've just seen, right? So we have the median. That's why I went through all the motions of going from mean, mode, median, right? I mean, that's I have my Q1 and Q3, and hence the height of the box, that is the interquartile range, right? So this is where 50% of the data lives. But, okay, what are then these whiskers? The whiskers are, well, partially defined by your own, in its sense, typically seen as a parameter, but it's a parameter that has a standard value. Namely, that is the distance that is 1.5 times the interquartile range, both in the north and to the south, right? Or east-west if you plot them horizontally, but I needed the space here on this slide. This you can interpret as sort of what is the reasonable domain for your data to live in, right? That's a relatively widespread already. And of course, the wider these whiskers are, well, the less clustered, less focused your distribution apparently is, right? I mean, so that gives you some insight. Then, last but not least, here we only have one of them. We have these circles, and they indicate outliers. And they're defined very naturally by, well, any value outside this 1.5 times the interquartile range beyond the third quartile, respectively, first quartile. So now you know how to read a box plot. Well, what if the data is more complex? I mean, so box plots are great, and they give a lot of insight. I mean, and if you have multiple variates, you can just plot them for all sorts of things at the same time, or not at the same time, individually, same time we get to later. But what if my data looks more complicated? Suppose that my generating function looks like this, right? So it's bimodal, 2 modes, 2 peaks, right? Coincidentally, they're actually not one with 2 Gaussians, one with, well, these parameters and these others. I mean, that's you believe me. If I would now generate data from this, and that I did, well, 2 years ago, I mean, then I have, for example, all these dots like this, right? I mean, it also shows that just plotting the dots, yeah, well, doesn't really give that much information, right? I mean, that's just by looking at this, or yeah, there is like, well, some density here, but here it's also an end here. Just by looking at this, because all these things overlap, it's very difficult to see, okay, well, where are now really the peaks of my distribution, right? I mean, that's, if naively, I would say, okay, there's a peak here, there's one here, there's one here, there's one here, there's one here, and I don't know where that one came from, but that was not the case, right? So we really need something a bit better. A box plot would look like this. Well, it gives you the impression that there's just one peak, right? Which is wrong. I mean, that's, so, well, we need to do something a bit better in that. So perhaps you say, okay, let's do a histogram, right? And that's, let's choose k intervals, and which value of k, well, maybe cross-validation, maybe you have some inspiration, whatnot. So you chop your domain into k intervals, and then you just simply count how many points fall into an interval, and that is going to be then the height of the bar, right? And that you could normalize this, that it sort of corresponds to a probability. And this is exactly also how many people see a histogram. It's essentially you're estimating the probability density function, right? But as we can see, this is a pretty bad estimation, right? This staircase-like histogram of the probability density function here, because we have, in this particular case, chosen too few intervals. Okay, well, we can crank this up, and now it starts to look a little bit better, a bit closer to the point. But a priori, I don't know, right? I mean, I can choose even finer grains, and then, I mean, you get this. Well, is this now good? Is this bad? I mean, is this now quadruple modal or not, right? I mean, choosing the right number of bins, choosing the right width of the bins, because right now I choose a equi-width binning. I could also have chosen equi-height binning, and I could. There's lots of options for dynamic things. I'm not going to go through all those motions. There's a whole research area that focuses on this. There are good solutions out there. Typically, yeah, the main thing that you should keep in mind that histograms are simply unsmooth. And for continuous valued attributes, it's not great because you need to choose the cut points, right? To translate it back to something like decision trees, but we also have like a hard cut, right? Those are highly variable, right? I mean, that's same thing with histograms. So we would like to smooth things out, right? I mean, that we'd like to get closer to the blue and the green bar over there. Yeah, so there's a question in that, is it a coincidence that Q1 is well, at the peak of this one, and that, yes, yes, essentially yes. That's that is. If I would have spread this out, then yes, that I could have screwed this up. I mean, that's screwed up your perception in any which way. Right now, just take it as a coincidence. Is box whisker the same as candlesticks? I don't know candlesticks, so maybe, but I doubt it, because it's really the standard name for this thing is a box whiskers plot or a box plot. Typically, you don't even mention the whiskers; you just assume that they have them. Okay, so let's try something different than the histograms, right? If the histograms are kind of meh, right? I mean, what can we do instead? I mean, so box plots not good if it's multimodal. Histograms not great either, and just plotting them, well, well, perhaps we can do a little bit better. Let me show you just in quick passing 2 types of plots that are useful in practice, right? You may want to use in practice, I mean, and hence it's very good to know of them, right? Dot plots and B-swarm plots. Let's start with the dot plots. If the number of data points we have is manageable, don't ask me what exactly this number is. Your mileage will vary, right? Then we can actually, with a small trick, we can plot them all. And not like we did previously where everything was overlaid, but by stacking them. Let's use some space in the width, right? Or in the height, right? Depending if we transpose it. So basically what we do here right now is you see, okay, well, we have 1, 2, 3 values of, is it 2.6 probably, whatever this value is. I mean, we have 3 of them. And rather than having some kind of bar, right, I draw them such that they just touch each other, but don't really overlap, right? And as a result, what you now get is that for these points, you kind of get a reasonable impression of what are the density functions, right? I mean, these are not artificially generated, like for me through some nice smooth function, but these are actually gene activations. And well, even if you're not a bioinformatician, and you don't even know what GATA6 is, I also don't know what that is, but you definitely see, okay, well, GATA6 clearly is happiest around, what is this? 4 something, right? 4.2, whatever. I mean, and at these higher values, I mean, well, much less happy, right? I mean, or much less likely to take this value. But, how do we achieve this? Well, we achieve this by overplotting. So basically, if we put stuff in the bin by just using the width, and well, we stack horizontally. So basically, it is a very fine-grained type of histogramming that we're doing, but we're just plotting the points themselves, right? And hence we achieve some smoothness. Now, what we can also do is do a B-swarm plot. And a B-swarm plot don't even use the binning, because histogram binning, right? I mean, we just plot all the points, but we just move them sideways so far until they don't overlap anymore. So it's essentially where previously, whoops, let me go back. Here we need to have the binning to say, okay, well, look, these are all the same value, right? And these are all the same value. And if we just completely skip that and just move things, if they overlap, we move them just sideways until they don't overlap anymore, we have a B-swarm plot. Looks still quite good, right? I mean, I still get an impression of the density in that. Now, of course, if you have many points, it becomes a mess, right? I mean, and especially if you have values that are very overcrowded, it becomes very wide, and then all sorts of problems happen. But B-swarm plots, I mean, I don't have the reference here anyway. I think these are from 2004, 2008, something like this. I mean, I need to dig it up. I mean, I forgot where the reference now disappeared to. But just to point out that this types of, well, research, because it's definitely research, right? And trying to come up with interpretable plots, it's really still ongoing in that. And I, of course, teach the basics here, right? Not the newest of the newest type of plots, because then I don't know if they're useful. But these you do see in the wild. Okay, now let's take a step away from just plotting things where they are, right? I mean, that's, or trying to chop them into bins. We wanted a more smooth type of, well, estimation of the density, right? That's what we want, right? And we've now seen a number of times that kernels are our friends, right? I mean, so why not use kernels? Okay, yeah, kernel density estimation. You ask, I deliver. In that, suppose that we're now back at our points, just like this, right? I mean, that's what is the probability? What is the density of 0.8? If I would just simply count, right? I mean, that's 0, right? I don't have any data point there, right? I mean, that doesn't really feel right. Depending on the width of my histogram, it will also be very low. And yeah, okay. If you remember what my curves were, actually the value there should be still relatively high, right? I mean, it was just a coincidence that no points were sampled there. But, so the problem is that if we really just look at what is the exact So if we just count, do we have a point at an exact value, then essentially what it looks like is this. Here at 0.8, it's empty, there's nothing, right? And if coincidentally, I mean, at the value of x1, let's just pretend it's 2, right, 2.0, there we have exactly 1 point. So this feels a bit stupid, right? That somehow the probability mass, right, so we have n data points, and where exactly we have a data point, it sort of has 1 over n probability mass, but all the space in between is empty. And of course, the more we zoom in, the more empty space there is, right? I mean, that's so somehow only points that we have seen have probability mass. I mean, that feels icky, right? I mean, that's we need to smooth this out. I mean, now how can we smooth this out? This is where the kernels come in. So rather than just saying, you know what, this has probability mass 1 over n, no, we're going to apply now a small little function. Let's use a Gaussian, because in kernels we always use Gaussians, or so it seems. Let's use a small little Gaussian and use that one with the mean at x1, right? And all of a sudden the data now looks like this. Now, the idea is that we spread the probability mass that we used to have at this peak over a wider range. And the Gaussian obviously has the highest peak right at the middle, and then the tails go out, right? Now, a Gaussian function has relatively heavy tails, and I also mentioned this in one of the previous lectures, meaning that no matter how far away you go, right, how extreme, the probability never goes to 0. It becomes ridiculously small, but it never goes to 0, right? Essentially, a Gaussian function, right? I mean, here, this kernel function, it gives the most probability mass here, but this little guy over here at the top, even for a value here at minus 2, 3, 4, it still gives a tiny little bit of probability mass, right? And that is a trick, because right now, every value on our domain gets some probability mass. That is neat. I mean, in many cases, this is actually what you not want, right? Because spread it out too far. But now we want this. Because what can we now do? We can essentially go over our entire domain. And now, for example, at this point that we wanted to query, 0.8, right over here, right? I mean, that's what we can now do. We just simply go over all the data points that we had, look at the kernel function centered exactly at that data point, and then ask this little function, how much do you contribute to 0.8, right? So what is the probability of a 0.8 data point under this Gaussian? And it will tell you, well, almost 0. Okay, fine, right? I mean, then we go to the next one. So, well, almost 0, but a little bit more likely than the previous one. And so on and so forth, right? And this one over here, right, that is relatively close, well, still will not give a lot of probability mass, but all these things together, I mean, well, give some probability mass for 0.8. If we sum this up, all these things over the entire range, this is what I get. This is what I get. This is the curve that I get if I do a kernel density estimate for this entire domain, right? So the trick is, once again, we have data points. On each of the data points, we apply this kernel, this function. And if we ask our model anything, we just have to look at the functions applied to the data points, right? We don't have an actual estimate for 0.8. We just ask all data points, well, how much do you like 0.8? That is essentially what it comes down to. Okay. Yeah, how do you compute this? Well, just normalized over all data points. And that I don't need to repeat. Which kernel do we use? Typically a Gaussian, but there are other options. I mean, there are other options in that. Basically, what you want is you want to spread things to the sides. I mean, sometimes you do want to have them cut off. You want to have compact support, all sorts of things. But the main thing is you want to spread your probability mass. Now, suppose that we take a Gaussian or some other function that looks a bit like it. Well, we need to choose the variance, right? I mean, the mean where it should be, that's obvious. I mean, at the data point, it would be a bit stupid to choose to place this function, if the data point is here, let's say, well, somewhere over here, all the way south, right? I mean, why would x1 give more probability mass to a much lower value? It's strange, right? So the mean is an obvious choice, but how much do we spread things out, right? So how peaked or how flattened is the Gaussian? Yeah, good question. Good question. And that is choosing the bandwidth of the kernel. And there are plenty of methods that guesstimate this for you automatically. So you don't really have to worry about this in practice if you just use one of these standard ways to do kernel density estimation. But it's also, even like in theory, it's not a problem. This would be normally a moment where I would ask you, I mean, okay, well, why wouldn't it be a problem? Can you think of a situation where essentially no matter what value of the variance I choose of my kernel function, right, as long as you use Gaussian, it's going to be fine. Okay, it's a bit more tricky to now have like a good interaction. I mean, that's so if somebody knows the answer, I mean, great, type it up. But I'm going to give it away anyway. That's the more data points I have, the less it matters how far away the probability mass has been spread, right? Because the more data points you have, well, it's been at the peak, it will still be the peak, right? I mean, that's and if I just get a lot of, so basically it flattens things out, but because I have so many data points, it will be fine. If I have few data points and have a very flat Gaussian, then my density estimate is just going to look like a plum pudding, right? I mean, that's so hence in theory it doesn't really matter, because in theory we have infinite data anyway, right? So these tricks on how to choose the bandwidth, typically they look at, okay, how many data points do you have? What are the distances between data points, and so on and so forth. Yeah, let me just mention that kernel density estimation is fantastic if you have one dimension. If you have multiple dimensions, well, you're in for a bad time. You're in for a bad time. That I leave it as homework for the interested reader to figure out why this is the case. Maybe I meet you again in another course. We can discuss this. Let's now put everything together. Now all of a sudden we know why we did medians and box plots and kernels and whatnot, right? I mean, that's which is the violin plot. So having the so this is the original generating function, right? I mean, the box plot, not really great. But now suppose that we get rid of the box, right? The box is kind of stupid. We keep the whiskers. The whiskers are kind of useful, right? I mean, this is still the reasonable, as you can see, the reasonable area for the data to live in. Perhaps this one could be a little bit more upright. Okay, fine with me, right? But what we want to get rid of is the stupid box, right? That George Box agrees. And if we replace the box now with a kernel density estimate, then we get this. And well, in violin plots, you can see why they call them like this, right? The violin is shape. I mean, that's we have now, hey, here's the big bump. This is the median value. And here, this, well, a bit more flat and a bit, okay. Maybe if we would have chosen our bandwidth slightly differently, this would have been more pronounced peak, right? But we get a much better view of our data, which is a simple box plot, right? So the violin plot essentially trumps the box plot in any which way. Although you don't see it as often in practice as you kind of should, I think, right? But now all of you know what a box plot is, so maybe we're going to see this much more in the future. Good. Okay, next up, what if we have multiple variables? Okay, then things become rapidly more complicated. I mean, I already said kernel density estimation, kind of sucks. Venn diagram, you know these things, right? You have seen them before. They're actually quite useful if you have 2, 3, well, actually from 2 onward. I mean, that's multiple binary variables, because then we can simply count how often, right, for example, how often do we only see, this case, I mean, TP53, so sort of protein, right? I mean, 44 times. I mean, that how often do we see both PTEN and TP53? 22 times, and so on and so forth. Okay, great, right? This is very, very nice. I mean, you get insight quite quickly. However, if you have more than 3 of these entities that you want to count for, things become, well, cluttered really, really quickly, because well, basically you lack dimensions. That's roughly what it comes down to. But also, it is impossible, some extreme corner cases aside, to get the areas right. Because look, this is, well, 22, this is now 5. Is this now really 4 times as large as this? Good luck getting that right? I mean, this is typically not good. So it's more intuition. I mean, one plot that I do like, and I have to say that I only came across recently, Nature Methods 2014, so only 7 years old, or 6, depending when they published in 2014, is the upset plot. You could say, haha, that I was very upset that I didn't know about it earlier. What is an upset plot? It's a histogram for binary features, but we now sort the histogram from high to low, or the other way around if you're so inclined. And then here at the bottom, we indicate which entities are we talking about, right? So now we can read relatively quickly that the most frequent, so 37 times, is just igvr. And for example, the combination of all these 5 things, 1, 2, 3, 4, 5, happens 0 times. Okay, and we have typically quite a bit of space in the width, so this works. Obviously, there is a clear limit to this, right? So this is for 5 genes. That works. If you have 6, well, 2 to the power 6 minus 1, because the empty set, maybe you don't want to plot. This rapidly goes out of hand, right? You have 80, you need 255 of those things. And yeah, okay, how useful is it then still, right? I mean, that's visualizing multivariate data is very difficult. Hence we go towards that near the end of today's lecture, where I'm currently driving towards. Suppose that we now have 2 continuous valued dimensions. Well, scatter plot. Right, scatter plot, just, I mean, that's the standard thing. I mean, that's, you guys also do this all the time. Now, scatter plot is fine if you don't have too many data points and you don't make a horrible choice in the color of the dots, right? I mean, like here, just blob, right? I mean, and especially make the horrible choice in colors. Right now, there's just one class, but if you have multiple classes and you need to check, okay, what are the colors? Do they don't contradict each other? And so on and so forth. Tung, why does the upset plot have its name? I honestly don't know. I skimmed through the paper. I liked the plot. I copied the name, but I didn't know. I don't know. I mean, that's like I said. Perhaps they were also upset that nobody else had thought of it. I honestly have no idea. It could be the bad pun that I just made. Maybe it's something else. I don't know. Okay, scatter plots. Bad idea if you have many points, but often you have many points. A bit of transparency can help. Already, we get a much better impression right now. What is the density of this data, right? However, how much transparency should you add or not, right? This has to be linear or what? You know what's even better? Let's just plot the density. Why not plot the density? I mean, that we all of a sudden don't need to worry about n anymore, right? We can have as many data points as we like. Actually, the more the better, because then we can guesstimate the densities. But yeah, if we want to estimate densities, then we're back into the histogram and kernel density estimation problem. Let me just put it simple. Which kernel should we choose and what bandwidth, right? So this one has a much smaller bandwidth. I mean, that's okay. This is probably good for the data you just saw. Is this now the best way to visualize this density, or do we rather do some color coding, the plotting style, right? I mean, okay, neat, but what is a not super well-known plotting type, but very useful in many cases, is the hexagon plot. In the hexagon plot, well, you still need to choose the size of the hexagons. But essentially what we here do is that, well, for every, let's say, well, hexagonal shaped thing, we just count how many data points land into this, and we color code accordingly. So a hexagon plot is sort of like a 2D histogram, but because of the hexagons, they're interlocking, they actually, well, get much closer to the shape of the data than if you would just have like, well, pixels, right, square pixels. Okay, so here I also give the reference to the Holmes and Huber book. None of these things I'm going to specifically query how would you build this or not, right? But I do want you to know that these plot types exist and, well, use them appropriately. And the take-home message is really look at your data, right? And that's in one of the earliest lectures where we looked at residual plots. I mean, I say we, but it was Professor Valera and you, but I mean, one happy EML family. There you also need to plot things, right? I mean, that's also scatter plots, and well, perhaps we can do some interesting things there. So that was a good example of look at your data to spot all sorts of problems or when it goes well. Good. So far, this was 2 dimensions. Let's crank it up. Let's go to more. Well, for my running example, I'm going to go through the enormous number of 3 dimensions, right? And don't be shocked. But you can scale it up arbitrarily, but then, well, the mapping, let's say, is this good or is this bad, becomes a bit more tricky in that. You have to believe me on my fancy beard. So what I have here on the left, at the top left, I have a spiral. I have basically blue and red, right? I mean, and it's sort of interlocking. It's a helix. What I can use, and one of the techniques that I will discuss with you, you already know it, but so I'm going to go through this relatively quickly, is to use PCA. If I use PCA to find 2 dimensions, to project down this high-dimensional 3-dimensional space into only 2 dimensions, and then plot the data in these 2 principal components, right? I get the plot here on the right. This is what it looks like. And whether this is good or bad, Yeah, well, it kind of captures the structure that you have over here, but it also doesn't really capture it, right? I mean, not because what is now the distance? This is really sort of like one of those beauty is in the eye of the beholder kind of things. So, of course, this spiral here, so this point here and that point here, so the blue and the red one, well, how far apart are they? And especially if I now, so let's say that this is now a distance of 1, right? I mean, that's so from this one to there, I mean, which distance is larger? Or is it equal? If you now look at the PCA plot, this puts the one at the peak here very far away from the red one, right? I mean, that's, but at the same time, sometimes it is, well, at completely the same distance. That is weird, right? I mean, so what is up, right? I mean, that's, in a way, intuitively, I mean, sort of this spiral goes here, this goes here. They should stay perhaps at the same distance, right? I mean, that's, okay. We'll go into that, right? I'm just pointing forward, referencing already some of the problems that you have with PCA plots. This is also from 1901, right? I mean, that's salmon mapping or multidimensional scaling. Perhaps you've heard it already. This is the second topic I'm going to be discussing in a few minutes. Salmon mapping, yeah, the footnote thing. Yeah, I'm sorry, but these are slides that I copied in, and somehow PowerPoint decided that, well, merging the the styles. Yeah, well, that's all of a sudden my footnote was a footnote, and well, this one I didn't catch. But I mean, I'm happy that you pay such close attention in that to the important details. Okay, so salmon mapping tries to fix some of the problems that we have in PCA. But, and well, salmon mapping or multidimensional scaling, 1969, nice. Then, much more recently, TISNE or TSNE. And this is, well, if I bend the truth a tiny little bit, this is the state of the art. TISNE plots is what you see in practice in many fields. If you have high dimensional data and not just 3-dimensional, many dimensions, right? And you want to sort of have a look at your data, what is going on, right? You use TISNE these days, or one of its slightly more efficiently computable friends like UMAP or whatnot, right? And what do we see here, and why do I like it? Well, look, we have this red string, right? And we have the blue string. This is basically, I would say, the manifold of this data. This is what is going on, right? I mean, that is the fact that it is like curly in space. Okay, fine. If it wants to do that, great. But this is the essence of it, right? It's an essence I don't really get from this. I mean, I don't know. It looks fancy, but I've got no idea how to interpret this. And PCA, yeah, I could have just projected it on 2 dimensions myself, right? I mean, I didn't really gain much in this example. Good. Okay. So this was all the forward referencing. Let's go to PCA. We've already seen this in dimensionality reduction, right? I mean, and we saw that it's not really a dimensionality reduction technique. Well, it's not really a visualization technique either, but you can abuse it as such. So what you hopefully remember is that in principal component analysis, the first principal component is that direction in your data with the highest variance, right? Such that if I give you the coordinate of a data point on this first principal component, you basically learned, well, the most variance. I mean, you home into it, I mean, where it roughly lives, I mean, as well as is possible with the 1-dimensional statement, right? I mean, that is what principal component analysis does. And what is the second principal component? Well, out of all the errors that we're still left, what is that direction, right? That explains the most. Okay, that is the second principal component. And we can keep on going, right? I mean, that's, but for visualization, that just clutters things up. So we typically go only for 2. Here we have an example of a heavy crimes or an arrest data set. And what do we have here? We plotted this data according to the x-axis, the first principal component, and the second one, the y-axis, the second principal component. And what we now have is if we now look at the first principal component, the loading factor of it, and what are the important attributes, the important features, or the predictors that it chose? Well, it assigns a weight of 0.5 to murder, 0.58 to assault, 0.54 to rape. Well, it's a very cozy little principal component, right? I mean, that's so clearly there's a direction of, let's say, the heavy crimes. The second principal component, after I organized my data into, okay, well, where is it, let's say, least nice to live, or if you're a psycho, where should you live? The second principal component that explains then the most, it puts the highest value on the urban population. So the second dimension tends to organize things to the more, how do you call it, more densely populated areas. In this case, this is states in the US. But, okay, so what we then also see is that you have, what do we have? Let's see, where are you? Where are you? Where are you? Well, we have the, so, oh yeah, California, I mean, Nevada is indeed, I mean, that's, so look, principal component, very high value, not a nice place to live, and not very densely populated, right? I mean, that, whereas, for example, North Dakota, and nobody lives there, I mean, nothing happens, right? I mean, you can be trampled by a cow, I mean, that's Vermont, same thing, you freeze to death, right? But that's, so that's really on the left-hand side of principal component one. And on the right-hand side, I mean, these are the places where, well, you need to be careful, right? I mean, that's, okay, this gives some insight, and it does cluster in a way those states together that show on these dimensions similar behavior, right? I mean, that's, so yeah, it gives you some insight, I mean, that's, okay. Is this really all there is to this data? Not quite. I mean, that's, but we're going to leave it more or less for now. How can you interpret PCA? I've already said this a few times, so I'm going to, well, I don't want to skip it completely, but I mean, define the loading factors. The first principal component, that direction with the highest variance, and the second one, well, it's the second, right? I mean, that's, it's orthogonal to that, because it has to be orthogonal, because otherwise we're not explaining the maximum number of variants. So one interpretation is if our data points are sort of scattered in this 3D space, the first and second principal component together define a plane, right? So from 3D, D-1 plane, on which if we project things on it, then we make the least overall error in predicting where things are. That's the interpretation, how you can look at it. And well, technically, you could call this, I mean, you could look at this as two different interpretations. To me, it's really the same thing. In that, you want to find that plane that maximizes the variance. I mean, not sure, whatever, because that explains most of your data. Now, what does the data look like if we project it, in this case, like that? And that, so this is some artificial data with 3 clusters. And as you can see, the points that, well, were generated by the same cluster, they tend to be grouped together quite well, right? So you gain some insight. But, okay. Now, one of the problems is that by directly trying to deal with this variance, points that are far apart in the input space, well, they're not going to be close in PC space because, well, high variance, right? I mean, they're automatically moved away far apart. That may not be so useful, especially if your data is not neatly standardized, right? I mean, that's if some attributes are just more variable, I mean, then that's all of a sudden going to soak up a lot of the positioning of the points, right? I mean, that's where points are going to be placed, because PCA really wants to explain that, even if there's not so much to be explained. As a result, by focusing on those far apart things, PCA says, okay, well, if things are actually local, I don't really care. I care about the things far apart. I mean, that is important. This is also what went wrong in the spiral picture. This is the salmon mapping one, but I mean, it rather focused on, hey, these things are far apart in my input space, and I want to keep it that way, right? That's okay, yeah, and I would say depending on the application, this is a big problem. I would actually say this is almost always a big problem. I mean, that's PCA is a nice first thing that you can do very easily, because often you already do a support factor, a singular value decomposition, and hence you can have a look at the first and second principal component as well. But yeah, it's not going to be your best visualization, so it's a cheap way out. Okay, so if this focusing on these faraway points is problematic, why not fix it? Why not try to find a mapping, a 2D mapping that tries to basically keep things that are close, right? I mean, rather than things that are far, right? I mean, let's flip it around. And that is essentially what multidimensional scaling is all about. It tries to find, I mean, so you have your input space in RP, right? So we have P attributes, predictors, and they're all real valued, right? I mean, that's x1 to xn. And what we now want, we want to project this down to a k-dimensional space. So our k, typically 2 dimensions, right? Because we want to look at it, and that. So we want to project these points onto, well, z up till n, right? That's on z, yes. Now, what we want to do is that if we now look at what is the distance in the input space, right? And we want in the projected space, we want to keep these distances the same or as similar as possible, right? But really the distances. So if things are close in the input space, try to keep them close in the projected space. If they're far here, okay, then far is fine. They don't need to be close, right? But focus more on close. Keep all the distances the same, which is a different, you could say, mentality than what PCA is trying to do, right? PCA is just trying, well, to minimize or to explain the variances away. So hence far is good in that. Okay, now, obviously, if we go from p dimensions to k, and k is much smaller than p, then it will quickly become impossible, just by triangle inequalities and whatnot, right, to maintain, if this is like this, these points are like this, and these, so we have a triangle here, and all of a sudden this is in, let's say, in 10 dimensions, and right now here we have only 2 dimensions. Well, we can't really position all the points such that all the distances between all the points are always the same, because we lost a dimension, right? I mean, that it's a bit the same. That so think of well, a cube, right? I mean, that and you have points, let's say, on the corners. If we now project it down to 2 dimensions, so like this or diagonally or whatnot, how on earth can we maintain that all these points remain equidistant? In the cube space, they were, right? I mean, the corners of the cube, they all have, let's say, well, except for the diagonals, but I mean, most of them have the same distance, just one, right? If it's a unit cube. But if we project it down, I mean, something is going to give, something's going to break, right? I mean, that's, well, this amount of breaking we call stress. That's, so, and we want, of course, nobody likes stress, right? I mean, also in MDS, we don't like stress. So we try to minimize the stress. I mean, that's, so the difference between the mappings of the distances. Well, it is, I'm not even sure if it's so the salmon mapping is the one that you want to use in practice, but Kruskal-Shepard has some nice properties, and it links very nicely to least squares. Because what are we doing? Well, we have our distance between 2 points, I and I prime, right, in the actual space. And now we look, okay, what is the distance between I and I prime in our projected space? Oh, and those should be the same. So let's, well, just take the square of that, sum it, try to minimize it, right? I mean, all of you now are either deeply in love or deeply in a hate relationship with least squares. So this one will at least be familiar. Now, in salmon mapping, we normalize these things, and that has the advantage of that. It's a bit less extreme. That's roughly what you can how you can interpret it. How do we now find these z's? I mean, how do we map these things? We do this by gradient descent. Basically, we try to iteratively move things around in that direction such that we minimize the stress. And we keep on repeating this for every point. And in the end, then we have a projection that we like. But, yeah, you can define it in eigenvectors. I mean, that, and in special cases, it becomes the same as a principal component. But in practice, this never happens. Now, the nice thing is that MDS, it actually doesn't care about the actual points, the actual data points. It only cares about similarities or dissimilarities, right? And why is this nice? Well, because there is, well, infinitely many similarity or dissimilarity measures that you can define, right, that people have defined. And, well, we can simply use them, get the dissimilarities per data point or per pair, right? And that's, and then just run MDS on these things, and we can compare what are the figures that we get. But, so there's not a single MDS, let's say, unique solution, right? But there is a good solution per similarity or dissimilarity measure. That you can even, this is also why we have the Kruskal version in the previous slide. You can also even do ranks. Then you don't even need the actual distances anymore, because, okay, if you can't really trust your distance measure to be equitable in the sense that this distance of this length is not the same as this distance of this length, because it's a slightly different part of our space, right? I mean, that's so I'm good friends with that person and good friends with that person, but a bit more good friends with that one, actually, blah, blah, stuff like that. Okay, so let me give you an example. Does MDS work in practice? And that's well, PCA, like I said, first thing that you can try, but not really what you should do. MDS, well, I like it, and I've used it quite a bit in previous papers. And that it's a good way to if you want to compare distances, dissimilarities between multiple things in a reasonably interpretable way. MDS is your friend in that. For example, here, well, genetic shift of influenza viruses, and that all sorts of things measured, right? I mean, original space 79 dimensions, not really something you can look at, right? I mean, that's even if you would just plot every, let's say, pair of dimensions, so 2 to the power 79, oh no, 2 to 79 squared minus a few. Anyway, very large number. You can't even look at all these projections, right? I mean, that, now, if you use MDS, then this is one of the plots that you can get. One of the key things is, and this is why MDS is not everybody loves it, it is stochastic. In the sense that we start from some point and the gradient descent, I mean, more stochastic, right? I mean, that, so the problem is not convex. I mean, that we basically run through our data points and our dimensions in, well, arbitrary order, right? I mean, that's until we find a local minimum. Yeah, so you need to do this multiple times and then look at the results and see which one you like best. And if you're lucky, all of them look great and show the same thing. And if you're short on luck, you get many plots that look like crap, and maybe there's some gold among them. What you can see here is that, so the coloring is done, well, with some additional knowledge, right? And you can see that it does cluster these different strains of viruses in that. So that is quite neat, right? I mean, but note that the labels, this is sort of like, well, post hoc imposed afterwards, because it's an unsupervised task. The task was not find a mapping that separates the colors, right? It's just the coloring that we, just look at, let's say, the colorblind version of this plot. You see these groups, and then, yeah, these groups are kind of meaningful. That's what this comes to. How many dimensions do you need? Well, that's because MDS, you can choose the set in any dimensionality, right? As long as it's lower than, so K, you can choose it lower than P. It depends on your problem. If you want to maintain the key information of your dissimilarities in the full space, you might need 2, 3, 4, 5, 6 all the way up, right? And that, so yeah, you can look at the stress that is left, right? I mean, that's and perhaps do like a cross-validation kind of thing over multiple runs. But typically, it's sort of like you have to try. And you know when you found something after you've done something. You know it when you see it. Good. Okay, now we get to the last method, Disney. And as you see, I mean, Disney gives the best result here. I would say, right? I mean, that's it really keeps in mind that all these blue points, in turn, they're very close to one another, and well, there is some distance to the red ones, right? And it also stays constant. I mean, this is what is not to love about this plot. To explain Disney, I have both 2 or 3 very formal slides, like I also had for MDS and stuff, right? But that's but I didn't like them, so I also made some fresh, very informal slides. Actually, I said I made them. Actually, one of my master students, Edith Heiter, did, and I asked her kindly, and now I blatantly copied it, right? So it's not plagiarism, right? I give the sources, I mean, that's but 0 points for me, although I still need to explain it. So, but in order to explain Disney, I first need to explain stochastic neighbor or neighborhood embedding, or SNE or SNE. I personally like SNE. If it's Disney, then SNE. What is SNE? SNE is a proposal by Jeff Hinton, and I forgot the first name of Roweis, but okay, well then it's just Hinton and Roweis, almost 20 years ago. Not necessarily so much to do with neural networks, it's differentiable. That is the link perhaps. And the idea is that we want to go from some high dimensional space X to a low dimensional space Y, right? Or I could have called it X prime, but Y, that's, so this is still, I mean, this is not the target, right? This is the low dimensional space. Typically 2 dimensions we want to visualize. But just like with MDS, just like with PCA, we can choose any dimensionality, right? I mean, your favorite number. And if it's 2, then it's mine too. Now, from the original data, we can obtain, by an appropriate choice, a distance matrix, right? So we measure the distances between all the points in this data. And I choose this as this folder because it can be anything, right? It can be sequences, it can be images, it can be anything, high dimensional, right? And now we want to do this such that if I look at the distance matrix, the distances on my down projected data, I kind of want these two to look similar, right? That's okay, hops. In particular, so and actually, if I were to say, okay, these need to be similar, these need to be the same, this is essentially what MDS does, right? Multidimensional scaling. Okay, well, between this data point 1 and 2, right? This intensity, I want to see this here too, as closely as I can, right? I mean, that's what we do in SNE is that actually we don't really care about the exact values, right? I mean, it's not that these distance matrices are sort of a goal to us. I mean, that's no. We want to have a projection that shows the local structure, it emphasizes the local structure, right? I mean, not like PCA, like just a global structure. No, we want to have the local distances, they should remain the same as much as possible. And what the exact values are, who cares, right? And that, now, the trick that they came up with is the following. From this distance matrix, we can infer a distance distribution. So what is the distribution of similarities or distances, right? I mean, that's for each point, or for this point, right? I mean, for this row, you have this distance, this distance, all these distance values, right? And we can get some distribution over that. Same thing for data point 2 and for 3 and for 4 and for 5, right? So we get a whole bunch of these distributions. And now I can do the same, or almost the same thing here, right? I'm going to look at what are the distance values for data point 1 in Y, right? And what are the distances to the other data points? And I can again get some distribution. And I want now these two distributions to be approximately the same, right? So if many points are close left, they should also be close right, right? And what the exact value is, okay, whatever, right? But the shape should be the same. That is the key idea here. I'm going to explain these things in turn. First, how do we go from a distance matrix to these distributions? Second, I'm going to do the same thing, but then for the down projected distances. It's going to be relatively short because it's going to be highly significant. And then third, how do we compare these two sets of distributions? Because that's what we need, right? In the end, we want to then sort of port this back such that we can optimize this mapping here, such that we have a low dissimilarity, right? Or a low divergence, a high similarity between the two things. Okay, let's first go into the high dimensional space. Still, the example is two-dimensional, otherwise the plot becomes horrible. But, I take every data point in turn. So I start with xi, so let's say x data points x1, right? Later I'm going to go to x2, x3, x4, and so on and so forth, right? For every data point in turn, which we're now looking at this one. And what I'm doing is I'm going to fit a distribution, a normal distribution, a Gaussian distribution that is centered around xi, my data point, right? I mean, that's and it has a certain variance. This is sigma, right? I mean, that's that is what these circles indicate, right? I mean, you can sort of see this as we have a Gaussian from the top, right? I mean, that's now this means that I give, if this is a Gaussian, right? I mean, I give more probability mass to this neighbor than I give to this one, because this distance is much shorter than that one, right? I mean, that's this is much shorter than that one. And this distance is again shorter than that one, and this one is furthest away. So this one I'm going to give the least probability mass. So in the end, right, the intuition is going to be things that are close or locally important in this space, I also want to see in the down projected one. So I would rather see this one close to me than this one, right? That is what it comes down to. That is the idea, right? Okay, that's it. Now, I want to have such a distribution, pi, for all my data points. And what I could do is that I keep all these sigmas exactly the same. I keep them fixed, right? So basically, I use the same Gaussian everywhere. Seems like a reasonable idea before you actually do it. And that's, because if we use the same variance for xj here, then, well, poor little xj is almost all alone in space here, right? I mean, that's, it only has, well, these people really far. I mean, this doesn't almost gets no probability mass, right? I mean, that's so in a way, this variance here, this stupid, right? I mean, xj is really choosing these non-existent neighbors to be close by. You know what? Let's scale up the variance of the distribution around xj such that actually we do give some probability mass to those that are most important to it, which are the ones closest, right? I mean, that's how do we choose this scaling. And how do we choose this such that for xi, I'm going back to slides, the variance is relatively small, and for xj, it's relatively high. How do we do this fairly? Now, well, in the paper, how did they define this? They define this by the perplexity of a distribution. So for each distribution, x, so pi, pj, yeah, so each of the points, we want the perplexity to be the same. What is the perplexity? It's 2 to the power of the entropy of this distribution. And the entropy, I mean, we have the definition. I have it in one of the next slides. I mean, so this is the downside of explaining things informally. But essentially what we count is that, okay, what is the probability of each of the points? And we then sum the probability times the negative logarithm of that probability. It's basically the number of bits that we need to spend to identify this point. That's how you can interpret it. That's this h of pi. And by raising it to the power 2, we get a number that becomes equitable. So by just choosing the perplexity, we essentially choose the variance per point, right? I mean, such that they have roughly the same number of points, roughly equally close by, even if that sentence does not make any sense. Because how on earth does xj have roughly the same number of points, roughly equally close by as xi had, right? Because a very different distribution. But by scaling this neighborhood, right? Okay. Hopefully that is somewhat clear. I mean, that's intuitively at least, right? I mean, that, so we're going to have now a distribution pi for every point xi, right? And hence also pj and whatnot. Now we go to the second part, the low dimensional similarities, right? How do we measure those? Almost the same way, almost the same way. We now call these distributions Q, right? Not to be confused for P and Q. And again, for every data point, we're going to have a distribution. Hey, it's again a Gaussian, right? And that, and now we sum over points yi, so these are the down projected points. But right now, what we do, we keep the variance fixed. We're not going to play this perplexity trick anymore, right? I mean, that's we want to have this variance fixed in the down projected space. Otherwise, things get completely out of hand. Okay. Now, because this variance is fixed, there's no, let's say, degrees of freedom and everything is easy peasy. There's almost nothing to understand about this slide. So how can we now compare distributions? If I now look, again, for one point only, right? So this is just for point xi. I look at the, I define this distribution and the variance based on the perplexity. That means that so where xi is, this is essentially here, right? I mean, that's, and of course, we only care about the one-sided Gaussian right now. So this point over here corresponds to this one, right? This one is that one, this one is this one, and this one is this one, right? That is essentially how they lay on my Gaussian, right? I mean, that's, it also means that xi really wants to have this point, when it sort of gives it the high probability of being a neighbor, right? This one gets a very low probability. It doesn't, if I get it a neighbor, great, but it's not going to make me particularly happy, right? And similarly on the right-hand side, we also have our Gaussian, but now centered around yi. And as you can see that, I mean, I try to make it subtle enough, but this point over here, that is, so this point corresponds then perhaps to this one, right? It's not exactly the same space, but it gets almost the same probability mass, right? Okay, so the two probability masses are the same. Hey, we're going to be happy, right? That this point over here corresponds to this one over here, got a bit closer. So it's a bit higher up in the on the curve, right? So, okay, is this good? Is this bad? So in the projected space, there's a higher chance of seeing it as a neighbor than it actually should. Okay. There's also the other example, but overall, these two distributions, they look quite similar. We don't want to decide it by just looking at these distributions. We want to measure this. How do we do this? We can do this by measuring a divergence. By looking at the cross entropy, or the Kullback-Leibler divergence in particular. Kullback-Leibler divergence is an information theoretic way of measuring how different are two distributions. Beautiful in theory, and in practice sometimes a bit cumbersome, but here actually it works really well. In that, well, it's remarkably useful in remarkably many machine learning instances. You will see KL everywhere, and that's even where you shouldn't see it. I mean, people tend to use it, just like sprinkle a bit of KL on top just to make it information theoretic. Okay, anyway, what does it do? What do we have as the terms here? I mean, let's start with this one. This is the entropy. So this is the amount of uncertainty, right? The chaosness, the chaoticness of the distribution pi. Okay, so that's basically the probability. How are these things distributed in that term? And here we have the entropy, the joint entropy over both P and Q, both P and QI. Now, if those are one and the same, then the trick is that if these are one and the same, then this one will collapse to basically either Pi or Qi because they're the same, right? I mean, that's, and H of Pi minus H of Pi is 0. Yeah? So if they're the same, these distributions, they give the same probability mass, fine. The more they start to deviate, then we essentially, because the entropy is the number of bits that we need to spend. So if this one gives the wrong answer, it assigns the, let's say, too little probability mass, then compared to what Pi want to do, right? I mean, that's and under Shannon information theory, less probability mass means more bits. So this value here will be higher minus low. So basically, the difference here is the number of bits penalty that we have to pay for using the wrong distribution, right? And this penalty corresponds to how far apart are P and Q distributionally. Again, I'm trying to convey the intuition, right? I mean, that's if you look at the book, I mean, they will have, or the specific paper, I mean, that's for this particular part, I recommend you to read the Van der Maten and Hinton paper on Disney, which I haven't referenced here yet because we're still in SNE, but we'll get there very soon. Because going from SNE to Disney is going to be like 1 or 2 slides only. How do you actually compute the KL? Well, it's over here. We go over every pair of points, and we look, okay, what is the probability mass for them being neighbors? And that is that. We do this again for every distribution Pi, right? And then for point 1, we have such a distribution, point 2, and so on and so forth. Okay, I'm already going to forward reference what goes wrong with SNE. So suppose that I have this point here, right? In my original space, like this is my bestie, right? Very close to me, right? I mean, that gets a lot of probability mass. I really want this as a neighbor, right? I mean, that's somehow in the mapping, right? In the lower dimensional mapping, we put this point quite far away. What does that mean? High probability mass. This means low entropy for this point. We need to, I have this person on well, if I'm old-fashioned, I would say speed dial. But let's say in my signal contact group, right, it will be at my favorites, right, really at the top, right? I mean, that's, and yeah, so it's very easy to reach this person. And that's, and here under the joint one, it's put very far away, right? So if I now use scroll, lots of effort, right? I mean, that's, so I get penalized quite a bit by putting this bestie far away, right? I mean, that's a big penalty, bad stuff. Okay, what happens, oops, if we do it the other way around? This person I know, right? It's somebody that I used to know. And somehow in my projected space, they got, well, really highly ranked. This means that normally I would pay a lot of bits. And right now I need to pay, well, roughly the same amount. I almost don't get penalized for this. There's essentially no reward for putting somebody who you don't call or text that often higher in the ranking, right? I mean, that's putting this person closer. So you want to have those people close in the input space, close in the output space, but the moment that they're far apart, we can always sneak them in. We almost don't have any penalty, right? That, so this goes already towards what goes wrong with SNE. Now, overall, what do we do, right? How do we optimize now the SNE embedding? We want to find that embedding Y, right? Placing all the points. Again, doing this very straightforwardly with gradient descent, right? The gradient has been written out, relatively straightforward to find yourself too. And what we now do is we sum over every data point. For every data point, we want to, well, so overall, we want to minimize this entire thing. We want to minimize the sum of KL divergences between the distributions Pi and Qi, right? So for each of these local Gaussians, right? I mean, that's, we want to see, we make them as close as possible. But, this is in a way how you can interpret this, the stress function of SNE. It's not really a stress function because it doesn't really want to keep the distances the same, but the distribution of distance is the same. I will answer your questions, Rafael, in a minute. So now we're at the formal slides, right? I mean, that's, I hope that you now got the general intuition. Let's speed through this. What is the key idea? We go from distances to probabilities. In the original SNE paper, this is what I follow here, so this is the hint and rows, they use conditional probabilities. In my intuitive explanation that I just gave, I already went to joint probabilities, which is actually something from the Disney paper, but in the end, it's equivalent. What I explained is easier to understand and easier to optimize. The key point is that Pij or Pjji is the probability that the data point wants another data point as a neighbor, and we model this with the Gaussian, right? And the variance is then defined by the perplexity. We want to find the mapping such that these distributions in the full space and in the down projection space are as simple as similar as possible in that sense. And hence we use a fixed variance. And whether you use 1 over square root 2 or 1, that is all equal. That is a small beer. How do we measure the agreement? Kullback-Leibler divergence. You can define it either as I did with joints or with conditionals. KL divergence is not symmetric. We've also seen this, right? Things that, well, P finds close and important, then Q better do that, right? And the other way around, yeah, well, I don't really care, right? Things that Q finds important, I don't care about. That is roughly what it comes down to. And this leads to a focus on returning local structure. We really don't care about the stuff in the tail of P, right? Yeah, okay, good. Yeah, you can interpret it as a floor space layout. Okay, the next slide, I organized actually the wrong way around. So there's nothing on the slide right now. You only have the stuff on the right-hand side, right? I mean, that's, and as you can see, well, this looks great because it clusters things exactly the way you want after you've applied the coloring. But just like in the MDS example, the coloring is stuff that Disney didn't know. We did this after the fact, right? These are the known clusters. So yes, it puts things together, right? I mean, that's cancer subtypes in this case, if I recall correctly, together in the right way. But if you now were to look at the color-blind version of this picture, which perhaps actually I should add next time around, yeah, then you have this one cluster in which it's impossible to see that actually it's 3, 1, right? You have this cluster, which is 1, okay, that's good. You would have, well, this big blob, which consists of 6 clusters, right, really? So, yeah, you don't really get, let's say, a high fidelity from your data. What you want is this on the right-hand side, right? Again, ignore the colors, but even ignoring the colors, look, well, you have a blue blob and you have an orange blob, right? I mean, it's even without knowing the colors, you can see the colors for all practical purposes, right? That is the result of Disney. But the right-hand side, that everything gets sort of crowded together, that is what you have with SNE. And, well, this is called the crowding problem. But where does the crowding problem come from? Links one-to-one with this unit cube I was talking about a bit earlier. So here I have a very simple explanation. Suppose that we now have high-dimensional data in 2 dimensions, right? We have these 3 data points. And, well, standard Pythagoras, distance 1, distance square root 2, right? But if we now project this data down to 1 dimension, so just on a line, well, what are we going to maintain? Do we want to maintain the distance from blue to red as 1, and from blue to red, blue to black, and black to green also as 1, right? That is this option over here, option B here. Or say, no, it's important to maintain the distance green-blue as square root 2, this option. Which one? Kind of tricky, right? And that's and what SNE does, I mean, it likes this one. This one is good, right? I mean, that's everything together. And that's whereas, well, perhaps we don't want to do this. And that's, so how do we solve the crowding problem? How do we essentially maintain these interdistances? It's a very simple thing. I mean, that's so in SNE, I was just talking about Gaussian, right? And that we have a Gaussian both on the distribution of distances in the original space and a Gaussian distribution on the embedded space. What is now the trick of Disney? Pay close attention to the right bump. Look, it's a t-distribution. And if we make it a t-distribution, we get t-distributed stochastic neighborhood embedding. And besides another one of the most highly cited papers ever, but I mean a very highly cited paper, because all of a sudden it starts to work. All of a sudden it starts to work. What is actually basically the difference? What did we do? Like in this Gaussian distribution, as we used to have it, the problem was that if points are in the tail over here at one moment, whether they're here or there, It really doesn't matter anymore. It really doesn't matter anymore, right? We just want to keep things here. This is what is important. And a t-distribution is a much flatter distribution. It's more heavy-tailed. So it tapers off much slower. It has the same shape, but it slows much. And as a result, there is still a much bigger difference. Let's say if at the same height here, right? I mean, here, you still have a lot of delta here left. And hence things can be positioned much better. That's roughly what it comes down to. So by simply shifting from a Gaussian to a t-distribution, all the machinery works. I'm not saying that is the only thing they did in this paper. They also proposed a few other things that I smuggled into the earlier intuitive explanation, like these joint probabilities. In the end, I mean, it comes down to the same thing. It just makes things easier to optimize, right? But everything is obvious once you see it. Yeah, and well, this helps to solve the crowding effect, which you also know what it is. Let me just show you a few instances why Disney is so popular in that. And for example, in bioinformatics, but in many medical domains in general, you have high dimensional data. You want to look at it, right? You want to see, okay, do we have clusters of patients or genes or this or that, right? Well, here we have so some word association data, language, right? Well, Popeye, spinach, cartoon, Beetlejuice, dill, pickles, or pickling. I don't know, I can't read it. I mean, that's a star, corn, scarecrow. Yeah, well, these are very different words, right? I mean, but semantically, they're very close, right? I mean, so there are now, I mean, with BERT and whatnot, right? I mean, that's even better embedding techniques for words. But this was really one of the bigger breakthroughs that all of a sudden, without just looking at the service level, like comparing words letter by letter, you can really see, hey, wait a second, they behave the same in my data. And look at them. So that's China dynasty and the Roman Empire, that these are the same, similar. Yeah, right. Now, one thing to point out is that this distance here between dynasty and China is not the same as, let me try to find, let's say, as interest and well-being. These distances are not comparable. They mean different things, right? Because they come from these different Gaussians in different densities with different perplexity. So it's not that these distances are comparable. One of the open issues. This is something that can give you a migraine, I guess. I mean, this is Netflix movies. And what do we see? Well, this is based on ratings. I mean, do people like movies or which ones do they like? And you see, for example, that Bad Boys 2, Rush Hour 2, well, those are arguably quite similar. They're grouped, well, close to one another and also as a group. Die Hard, Lethal Weapon, I mean, these are all, so I show my age right now. What is it? I mean, Fight Club, 12 Monkeys. I can't read the yellow one. Memento, so these are more like, say, the action, art housey movies, I mean, and so on. So makes sense, right? I mean, this is pretty cool. It's pretty neat. Now, an actual example of mouse brain cells and the typing thereof, right? Again, the coloring has been done post hoc. But as you see, the clustering effect, right, this grouping effect, this crowding effect is gone. All of a sudden, we have much more separated groups and hence a much better chance at actually finding relevant subgroups. You can also do this on images, I mean, the coil data set, I mean, different objects on the rotations. If you look at the Disney embedding, this basically are just really like the different rotations of one object. Whereas if you look at the salmon mapping, well, it's more like the explosion of all these things. And isomap and LLE, I mean, locally linear embeddings, I didn't discuss, and well, they have their place on the spectrum, but we're not going to discuss them, and I would not recommend them to use them in practice unless special conditions hold. Good. That's that. That was Disney, both intuitively and a bit more formally. And before that, salmon mapping and MDS, and before that, PCA, and before that, a whole zoo of different visualization techniques. And well, a little bit from last week, tubes in data, I mean, from kernel regression. Good. Let me have a quick look at the questions before I wrap up. I mean, what do I mean by local structure? That was one of the questions. I think that by now it's clear, right? I mean, that points that are close in the input space, we want to have them close in the output space. I mean, that's, just think of the spirals. Yeah, so the other question is, in the Disney function in R allows to optionally use PCA to get a low dimensional embedding. Why would we want that if it can mess up the original distance info? Yeah, that's a very good question. Are you interested in the original distance info? Or are you interested in explaining, well, variability, variance in your data? Where are, let's say, the uncertainties in your data? There's different ways how to look at things. And if you don't know what you're after, then, well, trying things makes sense, right? That just to get back to the residual plots, like the residual errors, right? I mean, that, well, looking at those, why would it make sense? You just want to minimize them. Well, if you do look at them, you can all spot all sorts of weird errors. I mean, heteroscedasticity, outliers, hard leverage points, and so on and so forth, right? So there, all of a sudden, we are interested in these highly varying points. So that is one of the examples why you might want to do t-SNE after doing PCA. In practice, well, I'm not aware that anybody I know has ever done that, but I can imagine scenarios where maybe they would want to. Good. That's it when it comes to the questions. So I'm going to say bye-bye. See you next week. And if there's any other further questions, I mean, well, either in the chat box right now or by email. Cheers. See you.